Hi everyone, good to see you again. I hope you had a nice and relaxing vacation, or if you did. It's a good conversation. I mean, just for general mapping of the, I don't know, the mapping of knowledge of where the fields belong to. Now we're sort of having a conversation about when we're invoking RE and R complexity classes. Now, not to be confused with this course, which is algorithmic complexity, length of programs. A field of theoretical computer science is called complexity theory. This is not what this course is about. Complexity theory looks at problem, how hard they are, and complexity classes. You might have heard of the complexity class P, NP, next, and so on. It's like, it usually relates with resources to carry a computation. Can you do this computation in polynomial time? Whereas we have not been interested in the time of computation, really. We just in the part of the computability theory course that we've seen, it was just like what is computable and what is not computable. That's what will be relevant for program size. Is there a program, yes or no? I don't really mind how long it takes. Now, complexity theory is the study of classifying the complexity classes, which languages can be recognized in what amount of time, what amount of space resources. And I guess that for our course, and I introduced it in the comment of the last question, I basically defined two complexity classes, which are the ones that are more linked with computability theory than with time or space or any other resources. They were R and RE. R is for recursive sets or decidable sets, so the set of all decidable sets. And RE is the class of all recursively enumerable sets, computably enumerable sets. And what else can I say at this stage? Now, it seems like RE is very large. It contains R. Is it the largest you can think of? No, there are larger complexity classes in which RE is an element, is a subset, but those complexity classes are larger. In fact, if we would have continued the part on computability theory, it would have been a next step. One way to define those classes is to say, okay, suppose that you have an oracle for the halting problem, which is basically you have a Turing machine and you have an oracle, just like in the movies, you can ask God a question, a binary question. Does Ti of j halt, yes or no? And it gives you the answer, the correct answer. So obviously this Turing machine via the oracle can solve the halting problem. Now, what can it compute and what can it not compute? And one can realize that, there's also stuff that it cannot compute, despite the fact that it can compute the halting problem. So that's one way to define the higher complexity classes. There's actually more elaborate ways to do it too. That was just a general conversation about, I guess, the field of computability theory and complexity theory, and we're basically playing where they meet with the complexity class R and RE. Mm-hmm. But yeah. Any other questions? Okay, let me start. I'll start with just a brief recap. It's been a few days. We've, I guess the main notion to recall was the definition of algorithmic complexity. So we called it X is a bit string. And we defined C of X, the algorithmic complexity of the string X, as the minimum overall programs of the length of the program. And it's not any program, it's a program for X. Namely, if you give that program to the universal Turing machine, it produces X. Now, I've said that, this is a universal Turing machine, but in fact, we require a tightly stronger result. We wanted that universal Turing machine to be additively optimal. Additively optimal, which meant that it could simulate any other Turing machine with only a constant overhead in program size. So most natural ways of writing down the universal Turing machines, like the one that we've written down, was additively optimal. But you know, as I mentioned to Aditya,
yeah,
I will get it right. Actually, I'm getting it right, but I like to double check Aditya. And yeah, there are like funky ways in which one could define a universal Turing machine, which is its programs are going to be super long. So if we're looking at length of programs, it's not very nice. So we just constrain ourselves to additively optimal universal Turing machines. And by using additively optimal Turing machines, they can simulate any other additively optimal Turing machine. So basically this measure here, yes, does depend on you, but if one would have come up with a different additively optimal universal computer, well, it would have given the same measure up to a constant, because they can both simulate one another with a constant overhead. Now a fixed constant, as opposed, and a constant in what? When we start varying over all x. So we've got, you know, infinitely many strings, but Cu and Cv of x will only differ by a fixed constant. Actually, the difference is not going to be fixed necessarily, but they don't differ by more than a constant. Yeah, for example, they may overlap on some strings and they may crisscross one another, but the absolute difference of Cv of x minus Cu of x is bounded by a universal constant. So this was our definition, and yeah, from now on we're going to be working with it. Maybe I start with just a useful definition. X star. Actually, the shortest program. For x is denoted x star. Another way to view it is that x star is the witness of C of x. Okay, C of x is defined via minimization. It's the minimal program, or the program of minimal length, namely the shortest program. Oh yeah, what's that program? It's a witness. It's called x star.
It's a P.
Yeah, x star is a P, correct. Yeah. If you will, U of x star is x. Yeah. It's just useful to have a name for this program. And maybe I should add, if there's a tie, if there's more than one shortest program, x star, we're going to take it to be the fastest one.
Oh, the fastest?
Yes, it will come up, why and how. If there is more than one shortest program, x star is the one with the least running time.
So U of x star halts in the fewest number of steps, basically.
Exactly.
We could halt in the same number of steps as well.
Okay, thanks. If that's the case, well then I will take x star to be the first in lexicographical order.
Okay.
This will be my last resort. I'm not even going to write it down, but I've said it. I cannot yet give the reason why, but take it for now as, oh yeah, we need one way of defining X star in case there's a draw. That's this way. It's gonna come up eventually. Okay, let me start with a first proposition, maybe first kind of computation that we can do with that, and it's just to make sure we have an upper bound for C of X. Okay, you can view C of X as a function. It maps every string X that we can understand as natural numbers if we want into some other natural number. It's the length of a program. Now we have an upper bound for that function. What is it? Proposition upper bound. For all string X, C of X is smaller or equal than any suggestion.
I have one. I'll wait a few minutes before I say it.
Oh, you have one. Okay. I heard one.
No,
You have a very boring complexity function.
God, I just have one. Now print X, like the length of print X.
Okay, print X is going to be our proof. It's good. So
Yeah.
so what does print X entail as a number here?
Was something, some epsilon, let's say, which is like the print.
Yeah.
function.
Great. Okay. You have the right mindset. Length of X plus something.
It's constant too.
Yeah, it's a constant. I'll just put plus O of 1.
Yeah.
Because this is the print, and this is the X.
Well, it depends on how you implement the print function. For example, if I have to take a little overhead for each bit, I would say big O of the length of X.
Okay, we're gonna make our definitions work for us in the actual proof. And actually, for this one, I'm gonna do two kinds of proof. One with Turing machines, we have an effective enumeration of Turing machines, and we're gonna have Ti of something, and blah blah blah. And then we're gonna realize, well, we're not gonna do Turing machines. We're not gonna program Turing machines. I've already said it many times, and I'm going to do a second proof, which is more like a high-level language that I encourage you to use if you need a proof of this kind of thing. And the high-level language proof is going to be the one print X. Okay, but let me first start with Turing machines, because this is how we've defined this thing here. And so the whole notion depends on Turing machine. Eventually, yes, as I said, invoking Church Turing, we're going to go like, if I have an informal program, it can be amenable to a formal program, which can be amenable to a Turing machine. And we're going to be happy with high-level programs. But let me just start with proof 1. Turing machines. And the Turing machine to invoke, okay, because maybe I have not recalled it, but we've seen the invariance theorem. And the invariance theorem was, we were arguing that CU, the argument that we used to say that CU is additively optimal as a measure is that U is able to simulate any other Turing machine. For example, the identity Turing machine. The identity Turing machine is a Turing machine. There is a Turing machine I call it ID or identity. Which computes identity function. You can simulate ID on input X. Because ID on input X will produce X. It's a Turing machine which copy its input, basically.
So your OL1 is just the length of the encoding of ID or whatever.
Correct.
Whatever index I need to call to reproduce the list of rules of ID.
That's exactly it. I'm making it explicit, probably for the last time. The program for you would be some P equals the encoding of IX, which we fix to be I bar X, where I is one index, where PI equals ID. And length of P, I'm sorry, I annoy myself with writing this here. I'm just going to do it here. Ti equals ID. And then what can we say about the length of P? Well, it's equal to the length of that string, which is the length of I bar plus the length of X. And the length of I bar, it's a fixed constant. It doesn't depend on X. I could have said, like, let X be a string. This is how I start my proof. And so it's the length of X is going to be my dominating term when X grows, plus O of 1. Now note that I bar is basically how I would program the Turing machine, the identity Turing machine. And this is how we're gonna, in the second proof, this is gonna be embedding the information for print, quote, X. When I write down on a universal computer, in modern computers, print, quote, something, it's like the modern version of writing down I, finding the index of the Turing machine, which does the identity calculation. It's just that who would really do that? Find the index of a Turing machine in the effective list of enumeration of all Turing machines. It's good to know that it can be done, but even if you program directly a Turing machine, you're not going to program I directly. You're going to be programming E of I or E of Ti, the rules of the Turing machine Ti. And then, oh yeah, these rules can be encompassed into a number in lexicographic ordering. But what matters is that I captures the idea of programming the Turing machine itself, the identity Turing machine. And what have we done now? Now we've just done, this is actually inequality, right? We've shown that there's a program P which has this length, and we want to show that this holds for all strings. Well, what we've done is that for all strings, we've exhibited one program to compute X. It's the program which invokes the identity Turing machine and then give it as an input X. That's one way of computing it, but it means that the minimal way of computing X is shorter than that. Okay, P is one program for computing X from U. Which means that the minimal program, or the program of minimal length, x star, that was his name, has length. Let's do it. Length of x star is, by definition, is c of x. The length of the shortest program is the complexity of x, and it is then smaller or equal than length of p, which was length of x plus O of 1. Questions? Okay, I say proof 2, but really you'll choose your, they're not radically different. In some sense they are, but yeah. I said Turing machines here, high level programming language. Print x is a program for x. And it has length.
Depends on how you want to define the length of
Yes.
characters, but yeah.
Length of x, if when x grows, this thing will grow. It will grow like the length of x, the length of this thing. The rest is fixed. Now, yes, I use the letter P, I use the letter R, and you can say, oh, should we encode that into bits, and what would be my programming language? And yeah, but you know that there's a pathway. There's a pathway to defining a proper programming language on a universal computer, one that we use, for example. Oh, and that by the church Turing, it's equivalent to a Turing machine. And so, yes, my first way of invoking this argument is, oh, if I can write this high-level language program, well, then I could also write a Turing machine. And you see the similarities. Basically, the constant size part of the program remains constant, both for the Turing machine and for the high-level programming language. And what grows is I have to specify x in this upper bound. Are there any questions? Okay, good. I'd like to clarify maybe something before we move on. Yeah. Recalling our identification of strings with numbers, it's worth writing it down. Well, length of x is equal to log of x floor. What does this equation mean? x here is a string, length of x is a number. I have to understand the left-hand side as a number. Or I guess I can understand it as a number. Now, floor of something is also likely going to be a number, so I have to think of it as a number. But what might be bothering is I took log of a string x. Oh, we have to think of, the string x is also identified with a number. And the log of that number. I take the log of that number, the number identified with the string x, and I take the floor function. Now, why does this hold? Let me just remind you the identification that we had. If I had a string x and its associated number of x, I'll say, epsilon 0 1 0 0 0 1 1 0 1 1 0 0 0. The identification of a string with a number was just to order them lexicographically and count them. So epsilon was my first string. Ooh, I'm going to put them closer. Number of x, 1, 2, 3, 4, 5, 6, 7, 8, and it goes on. Perhaps what matters more is the binary representation of that number. I could write binary of number of x or just binary of x. The binary representation of 1 is also 1, 0 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1.
1 0 1 1 1. Yes.
There you go. Okay. Maybe remind you, I've told you the trick that you can just put a 1 and then the string x. So when I write down the binary number bin of x, it's in fact equal to 1 and the string x. 1 and then nothing, 1 and 0, 1 and 1, 1 and double zeros, so on. But perhaps I just want to argue this in case it was not, it is not an obvious equation. We just have to work it out once. But once it's done, we're going to be happy to convert the length of the string x with the log of x, basically. So here, let me just write the length of the string x. This string is the empty string. It has length 0. This string is the string of, it has length 1, and so does that string. The next 4 strings have length 2, and the next 8 string will have length 3, and so on. Now with the log of that number, it's actually more convenient to have it written down in binary. The log of this one is, log of 1 is 0. Now it's easier to compute the log of powers of 2, right? This one is the next power of 2. This is 2. So it has a log of 1. This is 4. It has a log of 2. This is 8. Its log is 3. And so if I right away take the floor, this is going to be a number between 1 and 2, but the floor is going to be 1. And here I'm going to have numbers between 2 and 3s. The floor is going to be 2. And that's a very amusing non-proof that the length of x is equal to the floor of the log of x. But I think that this non-proof conveys more the idea than an actual proof. You could work it out for yourself. If you use this identification here, you're going to be writing this down as its binary expansion. It's going to be 1 times 2 to the power of n. if the length of x is n, plus the leading bit, and by the way, I'm going to be here writing x as x1, x2, xn. So plus x1 times 2 to the n minus 1, plus x2 times 2 to the n minus 2, plus plus xn times 2 to the 0. Perfect. That's what it means to write down a number like this. Observe that I have n plus 1 terms in my sum because I have n plus 1 bits in this decimal and this binary expansion. And if I take the log of that number, the leading coefficient will be n. Okay. Are there any questions? This conveys the idea a bit more easily. I guess this is too, if you really want to make something more rigorous, play with that. But I'm just being coarse here at the moment. All right, so what have we got? Another way I guess another way to write this is then, C of x is smaller or equal than log x plus O of 1. I'm absorbing the variations of the floor into the O of 1. And so if you really want to understand this as a function, it's upper bounded by the log. And intuitively, you might realize that it drops quite often. Because when it reaches a very neat string, for example, 1, 1, 1, 1, 1, 10 to the 10th times, its complexity will be small. But when it reaches disordered strings again, it's going to go back close to the log. Are there any questions? Okay, it's a good, I guess it's a good point to have a break. And let's reconvene in 10 minutes. The complexity, we've seen the complexity of a string. It might happen that a string is encoding a pair of strings. We can thus speak of the complexity of a pair of strings. The complexity of a pair of strings xy is defined with respect to a fixed encoding. That we've seen many times. Well, we've always been using the same one, but it could be, why not using the same one again? No. I prefer 0, 1 star. 0, 1 star. Cross 0, 1 star. To 0, 1 star. So we encode a pair of strings into a string, and the encoding is decodable. So if I give you that and I tell you, hey, it's a pair of string, please decode it, and it's been encoded via this function, you can decode it. So I left the definition up there because it's exactly the same. It's just that for convenience, I'm going to drop the D symbol. So I just write C of X comma Y equal, it's the minimal program of the length of the program such that U of P produces an encoding of the pair of strings X, Y. If I would have wanted to be economical in my definition, I would have just said C of XY is a shortcut for C of bracket X comma Y and bracket. That's what it is. Okay, well, we have this definition here, maybe as a game tonight, if you want to play this game. You can verify for yourself that, example, and C of X is equal to C of X plus O of 1. Right? When I write this down, it's implied that, for all X. And the O of 1 it's a constant, as opposed to growing with X, or growing with the length of X. It's a fixed constant. The reason why I bring this up is because now we have an equality. What an equality means, it means two inequalities. This is two things to show if you play the game tonight. You have to show first that C of X is smaller or equal than C of X plus O of 1. And second, you show that C of X is smaller or equal than C of X plus O of 1. And so by putting those two equations together, this one holds. Okay, so the arguments that we've been using so far have the form of an upper bound. If I want to upper bound this, I need to come up with one program for computing the pair XX. One program to compute XX is blah, blah, blah. And notice that blah, blah, blah has length C of X plus O of 1. Therefore, the minimal program for computing the pair XX is smaller than the length of the program we have just found. This would be an argument for point 1. And then you can, play a different game tonight and come back for point 2. It's like an independent question when you address point 2. In addressing point 1 and point 2 together, you can say, I'm done. I've proved that. Okay, I leave it unsolved for you to play the game tonight or whenever you want. Because we're going to see more powerful tools for which it's going to be trivial, and I think maybe you want to play this game. Okay, now we have the complexity of a pair. We have the complexity of a single object. Basically, there's nothing fundamentally new in the complexity of a pair, as you can see from this. You just need in the background a fixed procedure to encode a pair. But now I'm going to bring up a new idea. Because it's useful to say, oh, I want to compute the string x, but I have some auxiliary information. I have already, to my disposition?
At my disposal.
At my disposal, I have a string y that has been already given to me. And maybe y is going to be helpful to produce x. So I would like to be able to speak of the conditional complexity of x relative to y. The computation of a string x may be eased if some auxiliary information or auxiliary string, by which I mean information, y is given. Definition. So imagine that we have a Turing machine. It has a tape on which there is a program, and I want to accommodate the notion of there's side information there. There'll be various ways to define it properly, but I think that the one that is most intuitive is to, well, maybe stop being super picky with our notion of a single head Turing machine, and it just has one head. And in many contexts, we can invoke a Turing machine which has 2 tapes or 3 tapes, and it has as many heads. And so there's like a tape in which the auxiliary information sits. This will be y. It can just read the information on that tape, and there's a program tape on which P will sit, the program will sit to carry the computation. This is how I will encompass the notion of auxiliary information for algorithmic complexity. So the conditional complexity of the string x, or just of x given y, is C of x given y it's the minimum program of, it's going to be the length of the program, but it needs to be a program such that u of p produces x, but with a helper. The helper is the side information y. And note that now my universal Turing machine has 2 entries. We used to have only 1 entry, but we were always seeing that P as a concatenation of 2 pieces of information, namely I and X, Turing machine I on input X. This was our understanding of P. But now it has hard-coded another entry, which is Y. So I'll need to clarify this. Can I erase this piece here? Thanks. So where the universal Turing machine has been promoted to 2 tapes. The second entry refers to the tape of auxiliary information. Okay, so the computation model is basically enlarged. Has its power dramatically changed? No. It can actually be shown rigorously that a single tape Turing machine can simulate a 2-tape Turing machine. So whatever can the 2-tape Turing machine compute, the single tape Turing machine can compute it too. It's basically a useful way to understand, oh yeah, there is side information. And the side information is y. But we're looking for all ways, p, to produce x with y as a side information.
But P contains still the index of the Turing machine and X,
Correct.
and an input.
Correct.
So couldn't we just like use a 2-tape Turing machine also for?
We could have. We could have.
And also this changes the enumeration of Turing machines
It
because now we have Turing machines with 2 tapes.
Exactly. Exactly. So we have to backtrack a little bit and go like, oh, hang on, now my transition function, my rules that were defining my Turing machine, they used to be a function of what the head is currently scanning across the inner state. What was the inner state of the Turing machine? And then from this, the Turing machine executes either move to the left, move to the right, change the symbol. But now, as Lorenzo remarked, the rules are changing because now it has 2 heads. So the transition rules are what I'm reading from my first head, like the program head, what I'm reading for my auxiliary information head, and what is my internal state. And then, yes, I'm going to be either moving to the left, that head, moving to the left, that head. It changes the rules, but at least it permits me to state somewhat clearly that the auxiliary information is not embedded into the program. It just sits on a different register. Some authors will define this as only a single tape Turing machine. But then the argument is going to be an encoding of y, I, and x. But then we sort of lose a little bit the idea that y is side information. It's just sitting there. We have access to y. I prefer this one. But yeah, so it's not like a fundamental difference. Okay. We need to update this definition then, because now our Turing machines have 2 tapes. And by the way, I'm not scared of having Turing machines with 2 tapes because for prefix complexity, it's going to be super helpful to have a Turing machine with 3 tapes. Why not? It's no, there's nothing to be scared of. Now, so to update this definition, I simply need to add something here. what will be the natural choice? Empty string. Exactly. That's the empty string. Epsilon. And I'm still going to write it as C of x. C of x means this. It means the same as C of x comma epsilon. Okay, another example, which we're going to play with now instead of tonight. This one is for tonight. What is an obvious upper bound for C of x given y? Smaller or equal than something plus O of 1, as usual. C of x, correct. Right? If I give you site information y to produce x, you're looking for short computer programs or short algorithms. Well, one thing you can do is completely ignore it and produce x from scratch. Again, because one way to compute x with y or from y is to ignore y. And compute x from scratch. With x star. Okay. Questions? Yeah.
Yeah, somehow it's a bit tricky for me to understand what this side information gives us, because originally in the encoding of U, we could choose whatever ij, t Turing machine I on input j. So now if we had that case where we were not using a two-tape Turing machine, but we were actually appending y to the single tape one, isn't that just choosing a different input on which you're running sort of ti, but like on like say like a different input? So yeah, this somehow is feeling a bit tricky to me, that like why is this side information as opposed to just choosing a different sort of input string?
Yeah, okay. Y is fixed, and think of x also as being fixed. So fix x and y. And then the definition is a minimization over all programs for that. So implicitly, it's a minimization over all I and j's that are encoded into P, such that with help of y produce x. Right? So some intuitions that I could give. Now, this is not really an intuition, it's just a trivial upper bound that I can ignore y. But suppose that x is a complex string. We're gonna meet some complex string. Suppose that x is one of them. So its algorithmic complexity is large. Now it might be that y could be exactly as x, but every bit is flipped. Now if I give you y as a helper, it's huge resource, right? Because then the conditional complexity of x given y is very small. Because you could just write a program which says, take your auxiliary information y, flip each bit, and produce that as output. Well, flip each bit is a short program. Whereas the shortest program for x might have been very large in the first place. So this is where we start to have ideas of conditional complexity that can come in. But yeah, I suggest you think of auxiliary information as just another tape, instead of viewing as how it can be encoded into P, which, as I say, some authors do, but it's clearer here. In my mind, at least, in fact. Prove me wrong, please. If you come up with a new way of understanding this, and you come and see me. Great. Okay, yeah, now proposition. I'm going to give it a name maybe after. So, maybe you have the idea for a name. For all strings x and y, the following holds. C of xy is smaller or equal to C of x plus C of y given x plus an error term which is order of log n, where n is equal to the max of either the length of x or the length of y. Okay, what is that? We had, it looks like I'm trying to be fancy. We have three definitions so far. We've had the complexity of a single string, complexity of a pair of strings, and the conditional complexity here. And they're related to one another in this way. The complexity of a pair, xy, is smaller or equal to the complexity of x plus the complexity of y given x, plus something which is small. Why is it small? Because n is going to be either the length of x or the length of y, and then you take the log of that quantity. Right? Because usually, if suppose that x is the largest one, we've seen that c of x is smaller than n. It's smaller than the length of x. Now this error term is log n. So it's a much smaller order than the obvious upper bound that we've had for this term. Before we go and try to argue or prove, in fact, this proposition, do you have an idea of a name?
Entropy, conditional entropy, but with overhead.
I've heard some things in the front, but what was in the back?
Conditional entropy, but with overhead.
Yeah, okay. Conditional entropy. Yeah, that's conditional entropy.
And that's overhead.
That's the overhead. I've heard in the front what I was looking for. Chain rule. You might remember this from problem sheet number 1. But we had H written here. And we had H, and it was an equality sign. Okay, but we have something similar for complexity. And this is just one side. So, but yeah, chain rule is a good name. Chain rule, I'm going to complete the name as the easy side. Okay, so it's only one side of the chain rule. If it really holds, spoiler, it does, with an equal sign, this relation holds with an equal sign, well then there's two things to show, right? Like in your exercise for tonight. There's two things to show. When something holds with an equal sign and plus O of something, plus O of 1, you need to first show that, oh yeah, it holds one side. That's what I mean by side. It's like one inequality. And it holds on the other side. The other inequality holds. Now we're just looking at one inequality. This is why there's the notion of side. And as you can see, I wrote the name easy. It's easier to verify this side than the other side. Okay. Proof. Let me first tell you the generic idea before I write down the things. In fact, any ideas? It's the easy side. It's not really disastrously hard. It sort of gets tricky to find the error term and why there's an error term, but just the generic idea. We're looking for an upper bound for this quantity. So we want to upper bound the length of the shortest program to produce x and y with two things. The length of the shortest program for x and the length of the shortest program for y given x. So if we want to upper bound something, we have to give one way of producing the pair x and y. One way of producing the pair x and y, which involves c of x. So the shortest program for x, and c of y given x. So the shortest program for y, given that you've already done x. So what's the generic idea?
So you first compute x, and then you use x to compute y.
And then you compute the pairing. And you're done. Yeah, exactly. Right? So one way to produce the pair x and y is to produce x with x star. This will have length c of x. And then you have another routine somewhere else in your program, which says, oh, now that you've done x, and it sits on some auxiliary tape. Nice. Use this x to produce y with the shortest program that produces y out of x. This will have length c of y given x. And then you've done x on some tape and you've done y on some other tape. Go back and compute the pairing. But computing the pairing, the pairing function is a fixed prescription of how to compute the pairing out of what you've just computed.
So why the error term?
Because I need to put them together to make the paper, right?
Yes, but that's I mean, I would say that log n is the time complexity, but not the algorithmic complexity.
Let me do the proof. You will see where it comes in. And in fact, I'm making it longer than it should be to make it pedagogical for you to see that, oh, there's an error term. Because it will be one of our motivations to go to prefix complexity. Okay, proof. Let Q be the witness of C of y given x. Since I'm being pedagogical, I'm going to tell you what it means to make sure we have it in mind, i.e., the program of minimal length such that U of qx equals y. That's what it means by witness, right? This is a minimization. The witness is that p, which I called q, in fact, which has that. So it was like the x star when we had only one parameter. The aim is to construct a program for the pair xy for xy from x star and q. Right? I want to compute the pair x comma y, or an encoding of that pair, with x star, the witness of c of x, the shortest program for x, and also q, the witness of c of y given x, namely the program which, with helper x, computes y, and it has minimal length. Okay, so that's the aim. So if actually I have a program which involves x star, which involves q, it's going to have length of x star plus length of q, plus maybe something else. And this is where the something else will come in. Now, if delimiters were free, which is a big if. Delimiters a program for x, y would be R delimiter x star delimiter q, whereby delimiter I mean this one, this symbol. And now I need to tell you what's R.
That should be the length of x and q.
Sorry?
And that can be the length of x or q.
Uh-huh. Yeah, okay, by delimiters I mean like a third symbol. This is what I mean by...
The delimiter is the same as blank symbol, or is it another one?
Actually, it could be a blank symbol.
Okay.
But if you remind what we have as the definition of an input of a Turing machine, the input is made only of zeros and ones.
Okay.
And the blanks are like the beginning and the end of what's given to the Turing machine. So, in fact, another way to say it with Matteo's proposal is to allow for a program to contain blanks. But I'm not done, right? I still want you to know and read x star. But this changes the whole notion of what we have of an input of a Turing machine. Let me insist on something.
Takes why you don't do x star on one day and q on the other day.
Okay. This state is always fixed for the side information. I don't want to leverage, and my minimization is only over P. So I'm not, Y is fixed. It's like my side information. It's a read only. I cannot.
Why you don't put 3 dates then? You cannot like another one at the third one.
Yeah, but then, okay, how do I define the complexity again? It's going to be the length of the sum of all the programs, or
Just sum up like the programs on the two tapes that you can use. Without loop.
yeah.
Like-
If I would allow myself for 2 program tapes, I could say, yeah, this will be on my first program tape, this would be on my second program tape, and my first subroutine would be somewhere, but maybe it would work in this case. But that's not my model. The program is a fixed string. It's only one string made of zeros and one. Let me just stress here. If we're not gonna take it as yes, delimiters are free. By the way, if we take the delimiters to be free, it basically says our alphabet is no longer binary. It's like ternary. I have 3 symbols. So should we take the log base 3 and you redo the whole theory in base 3? Like, no, the point is to keep a binary alphabet. So that if I'm gonna have problems with it, I'm gonna say, well, delimiters are not free, my friend. What you need is a program to produce the pair xy that uses, yes, x star and q, fine, but it has to be only made of zeros and ones. But for now, just so you could see the argument, give me for now that, yeah, if delimiters are free, this would be a program for xy would be this. Boom. Where R does the following. Where R contains the following instructions. And I've briefly mentioned them orally, right? R would be a constant size program. It does not depend on the size of x star, it does not depend on the size of q, so it does not depend on x, it does not depend on y. And it would contain the following instruction. First, after the first delimiter, a program is given to compute the first string. It's x. And this string and should be stored on the auxiliary tape. Okay, so R contains the first instruction which says, okay, you're going to meet a first delimiter, and what you're going to meet is some program, execute it, terminate the computation. What you're going to have is your first string that you're looking for. Store it somewhere. And the second routine is, well, after the second delimiter, you have another program, Q, which, with the help of what you've just computed x, is going to produce another string. That string is going to be y. After the second delimiter, a program is given to compute the second string. y with the help of x. Which was already computed. I refer to x as the first string that has been computed. And 3, compute the pairing. XY. And halt. So basically this is what the preamble R embeds as instructions. And as I mentioned, note that R is of constant size. It's O of 1. It does not depend on X. It does not depend on Y. And so it does not depend on N. This N was chosen to be the maximal length between X and Y. Right? It's just a set of instructions of this kind. But as we've mentioned, this is not a valid program. A program is to be made only of bits, only of zeros and ones. And now I'm invoking free delimiters. I'm like changing my alphabet. But at least we have the gist of the idea. We can compute x and y by, well, computing x from x star, and computing y given x from q, and then computing the pairing. Okay. However, delimiters are not free. We need a single program P made only of bits. And for which U of P equals XY. So we already know that, well, we know, since we want to compute an upper bound for the shortest program for xy, and that this upper bound involves x star and it involves q, I'll be inspired by this construction, and I'll be looking for a P of the form if P is of the form P equals a different R, call it R prime, x star q. Basically, R prime is the same idea as R. It has the same aim. We want to be, it has to be like a short program, which are going to use two other subroutines to produce, well, first x, and then y from x. Well, the problem is that R prime will need to be able to tell apart this string. right? R prime is going to be a fixed subprogram, a fixed subroutine of short size. And then it's going to have a bunch of bits following it. But there's no free delimiters. R prime is not going to be able to know, oh yeah, there was a hashtag here. Should start an Instagram hashtag short program. Or hashtag. There was a dial? What's the name of this symbol?
The hashtag symbol, it has many names historically.
Yeah, okay.
When I was a kid, we called it the pound sign.
The pound sign.
Yeah. But
well, yeah, I don't have access to the pound sign or to the hashtag. I have dial in mind, but sharp, yeah, from music.
oh, also sharp. Yeah.
Sharp, yeah, there you go.
Although sharp is like tilted, isn't it? Sharp is like an italic one.
Huh? Okay.
This one, the normal one, is straight. Is it? I think if you do hashtag on your PC, is it tilted?
I mean, these slides are tilted. Those
No.
not.
Yeah,
But these ones are always
Yeah, these need to be tilted.
Okay, I learned something today.
Okay, anyways. So yeah, so once R prime is done, it needs to be able to tell apart, I've got a big bunch of bit and I have to be able to read which is X star and which is Q. And that poses the problem. So the preamble R prime, needs to do what R does. And moreover, it needs to contain some delimiter. In fact, delimiter information. In order to break X star Q, which is the concatenation of X star and Q, it's a large string, into X star and Q. One way of doing that, it can be the length of X star, which we know is C of X, given in a self-delimiting way. For example, as C of X bar. Thus, what do we find? Finish here. Well, what's the length of P? First step of computation is quite easy. I'll just write length of R prime plus length of X star plus length of Q. That's an equal sign. Another equal sign is going to be, I'm going to leave length of R prime for later. But the length of x star is by definition c of x. And the length of q was by my short definition of q. It was the witness of c of y given x. So its length, q was the witness of c of y given x. So the length of q is the c of y given x. And yeah, now I'm going to be using those with some error terms. And c of x plus c of y given x. Now what's the length of r prime? Well, as we've seen, r prime contains basically the instructions that were already in R, which is all constant size, doesn't depend on x and y. But we were annoyed by the fact that we needed to tell apart x star and q. And so the trick that we had found was to hard code into the program into the first routine, the preamble, r prime. We had to encode the length c of x in a self-delimiting way. And so let me just say, well, it's plus the length of c of x bar plus O of 1. Because all the constant size routines or constant size instructions, they fall into the O of 1. The only thing that it doesn't remain constant when x and y vary are going to be the delimitation, which was the self-delimiting encoding of, oh, no. No, it's correct. Yeah. I have to give c of x as a number in a self-delimiting way, and I want the length of that.
Should we include that in the previous steps as well?
Which steps?
The first two that we've written.
No, good question. I was like being very pedestrian in my derivation here. The first equality comes from basically this equation here.
Okay, so we just said, assuming that we can just divide them.
No, the program P is of this form. It's a bunch of strings that are concatenated all together, and these strings are the string r prime, which correspond to our program, our first preamble, concatenated with the string x star, concatenated with the string q. So the total length of P is the sum of these lengths.
Yeah, I thought like that we cannot distinguish them in the given sense.
Yeah, exactly. Well, I don't need to be able to distinguish them to write this down.
Yeah, because of the equalities.
Yeah, this is just the fact that, the length of concatenated strings is the sum of the lengths. Okay, so let be a bit. Let's finish this off. C of x plus c of y given x, and plus. When you have a number that is encoded in this self-delimiting way, it's 2. Hang on.
With 2 log of.
2 log of c of x, correct? Yeah. 2 log of c of x plus 1, but the plus 1 will fall into the O of 1. And now we've seen that c of x was smaller or equal than log x plus O of 1. Oh no, this is not what I want to use, sorry. Smaller or equal than the length of x plus O of 1. This was one of the first things we showed today. And so it's smaller or equal than the max between the length of x and the length of y plus O of 1. So it's smaller or equal than n plus O of 1. But then I'll take the log on each side and I'll be able to bound this by The first term doesn't change, the second term doesn't change, plus 2. I don't even need that anymore. I think just O of log n does the job. I'm absorbing this constant into the order of log n, and C of x is smaller than n, and so the log of C of x is order of log n.
But then why do we need to upper bound the length of x with the maximum between the lengths of x and y?
Ah,
It seems just a free...
it's a good point. Yeah.
Because of the symmetry, probably.
Yeah. Okay, I was being too conservative here. In fact, I could have taken the minimum. It would have been more interesting.
Because actually, you can take you don't have to put it in that order. For example, you can put Q before, and then you encode Q. Example, if it's shorter.
Yeah, I could do exactly. If Q is shorter, or yeah, this is why. Well, this is why the minimum is a bit.
Sure.
Yeah.
The minimum is...
The real story is that I want something short, something neat to express the error term. If I want to go into the minimal bound, probably here I would stop. This I need to hard code C of x. In fact, yeah, I should stop here, but. We can play with how close I find the bound, and I need to grant you that I didn't need to take the maximum. I think I wanted something neat. What's the largest string between the two, and this will be my error term. In fact, clearly I could have taken the minimum by choosing either which. Do I do y star and then q, or do I do x star and then q?
Guys, I hate to cut off the discussion, but I think there's a class.
Sorry, yeah.
It's 4:30, so I think
Okay,
we're supposed
sorry
to
about that.
start.
Yeah. Okay.